Hi, I'm Michael Gourlay. I want to tell you how I added the appearance of detail to the terrain of a planet in a game I'm working on. I use the common technique of modulating vertex colors with a repeating detail texture. The texture coordinates I use have a special property that lets you tile a square repeatedly onto a sphere. I call them mirrored octahedral coordinates. How can you add apparent detail to planetary terrain? Let's start with a simple case and work toward this more complicated case. Here is a quadrilateral terrain without a detail texture. This shows the same terrain geometry with a detail texture applied once. It has 256 by 256 texels. This looks slightly more interesting than terrain without any detail texture, but this coarse texture does not add enough detail. You could increase the resolution of the texture, but to get enough detail, it would take too much memory. And if you wanted to make the terrain geometry larger, you'd have to spend even more memory on the detail texture. To give the appearance of finer detail, you can repeat one texture over and over across the terrain. This shows the same terrain with the same 256 by 256 texture we used before, but repeated 32 times along each direction. That's a total of 1,024 repetitions of the same texture. Now the terrain looks like it has more detail. I'll explain how this classic approach works. Whereas simple texture coordinates u and v go from 0 to 1 in each direction, this geometry on the right uses texture coordinates outside 0 to 1 in each direction. We tell the renderer to interpret texture coordinates outside 0 to 1 to wrap to inside 0 to 1. This is called wrap addressing. To make a 256 by 256 texture spread across a region with the same apparent detail as a 2048 by 2048 texture, we would apply texture coordinates in the range 0 to 8 along each direction, because 2048 divided by 256 is 8. That's how to repeat a texture on a planar terrain. But how do you repeat a texture on a spherical terrain? For that matter, how do you apply texture to a sphere at all? First, let's look at some simpler cases. Here is a planetary terrain with no detail texture seen from far away. And here is the untextured planetary terrain seen from closer. And here is a planetary terrain with a non-repeating detail texture. And here is that zoomed out. As with the planar terrain, applying a single coarse texture adds a little detail, but not enough. Still, we need to understand how to apply a single texture before we can think about how to repeat it. There are two typical ways to define texture coordinates on a sphere. Here is the simplest approach. You assign each vertex texture coordinates u and v in the range 0 to 1, just like with planar terrain. You can say u equals longitude and v equals latitude. This layout is called equirectangular. In this scheme, v equals 0 is at the south pole and v equals 1 is at the north pole. So v equals 0 is at the opposite side of v equals 1, just like with planar terrain. Note, however, that in this spherical case, u equals 0 and u equals 1 refer to the same location, like the prime meridian. This layout has a peculiar issue. Texels at the poles are compressed into a single pixel. Equirectangular textures have far more resolution at the poles than is necessary. So textures used this way look stretched at the top and bottom because they get compressed horizontally when applied to a sphere. Because the equirectangular layout involves drastically non-uniform distortion at the top and bottom, a single texture could not be viable as a repeating detail texture. This shows what can happen if you try. You get distracting artifacts near the poles. The other common way to define texture coordinates for a sphere uses a cube map. you use 3 coordinates, u, v, and w, which is a unit vector indicating a direction. That direction from the sphere's center implies a point on the sphere's surface. Note that u, v, and w are not entirely independent. If you choose any 2 components, for example u and v, that determines the other component up to a sign. We'll return to this in a moment. Meanwhile, this diagram shows how to map from a point on a sphere surface to a point on a cube face and vice versa. How could you make a repeating texture scheme from a Cubemap texture layout? You could repeat texture coordinates on each face of the Cubemap, treating each like a square. That will work within each square face, but a problem would happen at some edges. That is a fundamental problem with how to tile square textures that do not have diagonal symmetry. I'll explain. First, notice the artifact along one edge and at that peculiar corner. This close-up reveals a clue to what is wrong with trying to repeat tiles on faces of a Cubemap. The pattern cannot continue across the edge between some faces, and no layout of this texture could fit into this corner. Pondering this problem led me to ask, can any regular, that is platonic, solids have their faces colored either red or blue such that each color only touches the other color, or katak? If so, then each of those faces could alternate UV values of all its neighbors, and within that face the UVs could duplicate unit values by an integer amount. This shows that the cube does not have this property. If you pick any face and color it red, all its neighbors have to be blue. But those blue neighbors then must have other blue neighbors. Therefore, a cube cannot be katak. This same is true for the tetrahedron, dodecahedron, and icosahedron. This shows that the octahedron can be katak. If you color a face red, then all its neighbors can become blue. Then all those blue faces can have all red neighbors. So an octahedron can be katak. Other triangular tilings have the katak property, but the simplest is the octahedron. An octahedron is made of triangles. You could just tile triangles and use half the square texture, but there is a way you can use the entire square. Folding and unfolding an octahedron provides a simple way to map between a square and a sphere. This property turns out to be useful for encoding normal vectors. These simple formulae convert back and forth between a pair of values in 0 to 1 and a unit vector in 3D. I won't dwell on this code. You can return to this slide later and pause the video, or just look it up online. How does the octahedral map help with repeating a texture on a sphere? Since the entire octahedron has its surface defined in the unit square, applying an integer scale to the texture coordinates u and v results in the surface of the octahedron repeating the same texture along each direction. Note, though, that the folded flaps need to have continuous UV values across their edges to adjacent flaps. That continuity can be imposed by mirroring the UV values when crossing the center lines of the unfolded octahedron. This shows mirrored octahedral texture coordinates applied to a sphere. The left pane shows the UV layout of the geometry. One instance of the texture is shown in the lower left of that layout. The right pane shows the geometry with the texture applied. Vertices highlighted in orange show mirrored edges. That mirroring vaguely resembles how, in a flat plane repeating texture, a texture can be made to seem like it tiles by using mirror addressing. For every other replica of u and v, flip its sign. This sphere applies the same detail texture 32 times in each direction on each half of the octahedron for a total of 2048 repetitions of the tile. That adds a lot of apparent detail while only costing the memory of 1 256 by 256 texture. By the way, you might have noticed that the texture map has some distortion concentrated in some places. That can be reduced with a simple warp function. The warp distributes vertices more uniformly, and UVs come along for the ride, so the detailed texture looks less distorted also. This shows head-on and side views of a sphere built from projections of a tessellated cube. It reveals a comparison between different mappings and how the tangent warp has less distortion than the straightforward projection. Moving vertices impacts collision detection, and the unwarp has to be applied then, and it costs too much CPU time, so I eventually removed the warp and unwarp. Perhaps the UVs could be warped without warping the vertices, thus avoiding the cost and complexity in collision detection. In summary, this is how I applied a repeating texture on a planetary terrain. This scheme seems to work well enough, and I have not yet run across a scheme I like better, so for now I plan to keep it. I found several other posts on the internet discussing the same kind of problem. I didn't find anybody else who used this particular approach, so maybe this is novel. If so, I hope that by sharing it, somebody gets some use out of it. Or maybe somebody will tell me a better way to do this. By the way, this video shows a planetary terrain and some boulders. They were procedurally generated. Lots of posts and papers describe solutions to that problem, and several published games use ProcGen planetary terrain. One of the classic algorithms used on planar terrain is the so-called diamond square algorithm. There are more popular algorithms nowadays, but I like certain properties of the diamond square, so I adapted it for use on a cube or sphere. It's separable from the detailed texture problem, so I won't cover it here, but maybe I will eventually make another video to describe how I did that. The results are arguably not as good as other techniques, but I had fun solving it. It turns out to involve a lot of bookkeeping, which is what this weird diagram is all about. Maybe I'll explain it in a future video. I hope you found this video useful or interesting. Please leave comments giving me feedback and how I could improve future videos. Thanks for watching. If you like this video, here are some links you might also enjoy.